Thermodynamics deals with equilibrium states. Now, what is equilibrium and what is a state? Okay, a state is basically a condition of a system described by a set of properties. So, for example, when you know that the pressure is atmospheric pressure and the temperature is 0 degrees, we know for sure that water will exist in ice form, okay, in solid form. So that is the state, right? It's a condition described by the set of properties, which are pressure, temperature, etc. A system can have different states. So this is the same system. Okay, both have mass of 2 kg. They are inside the same piston, same temperature, but their volumes may be different. Okay, and how is this possible? Because this is a piston, so you know that the volume can change. But what else changes? In this case, when you have a smaller volume in a piston, you have higher pressure here because of the compression and lower pressure in this state 2. Okay, that is an example. Equilibrium now is a state of balance. It doesn't mean that the system can't change. It doesn't mean that it's stable as in it can't change, but it means that it is no longer reacting. So, for example, from state 1, it reaches state 2, and it stays in state 2, right? It doesn't expand even further. So that is an equilibrium state. And we only study equilibrium states. We don't study a state that is changing over time. Now, a popular equilibrium state is thermal equilibrium, where the temperature is the same throughout the entire system. So take a look at this example. Initially, this is the tank. Okay, it's a closed system. Let's say it's a tank. It's a high temperature at the bottom, 42 degrees, and lower temperature at the top, 20 degrees. But eventually, you know that the temperature is going to stabilize. It's going to have an equal temperature throughout the system. So that is in the second state. So this is after reaching thermal equilibrium. Okay, and it's impossible for us at this level to study this state. So we study the equilibrium state, right? Now, there are other equilibrium states, mechanical, phase, and chemical equilibrium, but we're not going to focus on that this chapter, okay? Now, let's look at processes and their definition. A process is basically any change that a system undergoes from one equilibrium state to another. Look at process as you going to class, for example. From home, you go through a process to reach college. Okay, that is a process. And a path is the way that you take to go from one state to another. Did you take the highway? Did you take the LRT? Okay, did you maybe take a ride with a friend? So that is a different path that you may take to complete the process. Here's an example. Okay, state 1 is the initial state and this is the final state. This is one process path. As you can see, you can create as many lines as possible between state 1 and state 2. Okay, so in order to describe a process completely, one should specify the initial and final states. That would be the points, these black dots, as well as the path it follows. Okay, is it this curve or is it another curve? Is it the highway or is it LRT, right? And the interactions with the surrounding. Okay, in the case of traveling to college, obviously, it matters how long you take, how much you have to spend in order to go through that process, right? So all this information are important to describe a process. Now in thermal, we have something called the process diagram that should make it easier for you to see these processes. Okay, on the process diagram, normally it's pressure versus volume or temperature versus volume. All right, those are the two diagrams that we are going to use most in this subject. For example, this is PV, pressure and volume. You also have initial and final states. Now let's look at this. This corresponds to the piston that you see at the bottom here. All right. Initially, it has a certain volume. All right. You can see that the piston head is at this position. This corresponds to quite a high volume. So this is V1, initial state. How do we know this pressure? It's just any pressure, right? Just mark it at any pressure. Now, compression happens. You can see an arrow here meaning force. So compression happens to reach state 2. State 2 has a reduced volume, right? Because you can see that inside is the system. The system is not the whole thing. It's whatever in the closed compartment. So state 2 has small volume but high in pressure. How do we know? Because of compression. Okay, of course, when something is compressed and the mass doesn't go anywhere, it will increase in pressure. So this is an example. And of course, you can draw the process path from this. Now, you might be wondering why it's curved, why is it not a linear line, etc. Why is it not curved upwards? So we will discuss that in later chapters. Chapter 4 actually. Okay, so be patient. Now, the prefix ISO is often used to designate a process for which a particular property remains constant. Okay, so when you see ISO, it means something is constant. Okay, so here we can have isothermal process. That means the process happens at a constant temperature. Right? This is a very popular word. You're going to use it throughout Thermo. So please take note. Might have isobaric. Okay, isobaric, less popular. We always describe isobaric as constant pressure, which is what it is. Okay, but probably this word isobaric will be less used compared to isothermal. Isochoric, or isometric, I think, where the volume is constant. So isometric, I think you might recall this from your drawing class. So you have isometric drawing. So isometric is 3D drawing, right? And you drew it according to the dimensions. So that's why it's constant volume. And finally, a cycle is when you have a process that has the same initial and final state because it goes around and go back to where it started. So that's why it's called a cycle. Okay, a little bit more. We have temperature scales. So in this subject, we're going to use Kelvin and degrees Celsius. So the conversion is when you have a temperature in degrees, you just add 273. The 0.15 is optional. Okay, so for example, if it's 0 degrees Celsius, it's 273 Kelvin. If it's 10 degrees, it's 273 plus 10 Kelvin, which is 283. As simple as that. Okay, just linear addition. However, take note, all right, when you are dealing with change of temperature, then the number will be the same. For example, the change in temperature, which is written as delta, whenever you see delta, you know that it's change. Okay, T2 minus T1. Change in temperature for Kelvin will be the same in change in temperature for degrees Celsius. All right, so to understand this, why don't you try proving it yourself? Okay, if you have any problems or you're not clear, we can discuss it in the virtual class. Now, finally, another important property to discuss is pressure. Okay, we know that pressure is force over area, and the popular unit you use is Pascal, which is Newtons per meter squared. Okay, these are other units of pressure. There's bar, there's ATM, okay, 1 ATM, 1 bar, kPa, MPa, etc. But in this subject, we're going to use a lot of kilopascal, kPa, which is this times 1000, and megapascal, which is Pascal times 6000. Okay, and there's gauge pressure, absolute pressure, and vacuum pressure. Okay, so to fully understand this, I think we will go and look at it in the next chapter. Right? In the meantime, if you have any questions, note them down and we can discuss in the virtual class.